so far.
So section 7 is about linear, quadratic, and exponential models. We've already done linear models. That was back in chapter 5 when we were talking about scatter plots. So we've also talked about exponential equations before. We've kind of talked about exponential models as well. So now that we're dealing with quadratic equations, it's time to talk about quadratic models. So we're putting all of those together in this section. And here they all are kind of on this little take note. So we're going back to working with data. If you have data, remember that when you look at the data on a graph and you want to put a model to it, so that means make like a trend line. The trend line does not have to go through the data perfectly. It can just come really close to all of the data points, but it does not have to necessarily go through any of the data points. So the same thing is true of any model that we want to make. If we want to make a quadratic model, it just needs to come close to all of the points. It does not have to go through exactly all of the points or exactly any of the points. And the same thing is true for exponential. That's the point of the model. It's just representing the data as best as possible. So we are going to look at scatter plots again, but the scatter plot can be a line, it can be a parabola, or it can be the exponential. Remember what I talked about with the exponential? It comes very close to the axis here, but it never crosses, it never touches. It kind of takes off and goes up for forever. It winds up looking kind of like a hockey stick, okay? All right, so we have the model equation sitting here, the linear model, y equals mx plus b, that slope-intercept form. We have the quadratic. This is standard form for the quadratic equation, ax squared plus bx plus c. That's what we've been working with for 2 chapters now. And then the exponential, remember this one. A is the starting value, and then b is the base, that ratio that we multiply by every single time to get the next number. And then x is the exponent, okay? A lot of times we call it t because it was like how long we're letting the thing gain value or lose value or whatever it was, okay? So now we know that. To choose the best model for the data that you're dealing with, all you do is you make your scatter plot. So plot all the data that you have, or ordered pairs that we have here, and then look at it and say, oh, this kind of looks like a line, or this kind of looks like a parabola, or oh, this kind of looks like a hockey stick, and then decide, okay? So that's what we're going to do now. So graph each set of points and decide which model is the best. So for this one, we have 1, 3, and then 0, 0, and then -3, 3, and then -1, -1, and then -2, 0. So we look at that and we say, all right, would we draw a line through this? No. What does this look like? It looks like a quadratic situation. It looks like a parabola, okay? So we would model this using a quadratic model.
Is there any times where you can get like confused between either or?
Yeah, sure. We'll see an example where it could be something and it could be something else, but the math will lead us to what it actually is. Okay? So for right now, we're just kind of looking at it and saying, this kind of looks like a quadratic, so that's what we're going to go with. Okay? The second one, again, 0, 2, and then -1, 4, and then 1, 1, and then 2, and then 0.5 is like 1/2, so halfway up there. So yeah, so we see the curve here. Now, lines are not curved, so I would probably not go with a line. But could I fit a parabola to this, or is this more like exponential? So yeah, like on this one, we saw the definite turning around like a parabola does, right? On this one, we don't see the definite turning around like a parabola does. So could it be that we just didn't have enough data to where this thing turns around like a parabola does? And that's possible. But what you need to do is you need to look at the y coordinates, okay? Back when we were talking about exponential stuff, the exponential gives itself away when you look at the y coordinates and you see that we're multiplying by the same number every time, okay? So if you just look at the y, what's happening as we go from here to here, and then to here, and then to here? Or if you just look at the y coordinates, how do I go from 4 to 2 to 1 to 1/2. What's happening each time? I'm dividing by 2. In other words, I'm multiplying by 1/2. We're always multiplying, okay? Did I multiply by 1/2 every single time? Did I cut 4 in half and then in half again and then in half again? Yes, okay? And that is the dead giveaway for exponential every single time. So this one is exponential. And that's how the math is going to lead us to whether it's exponential or something else, okay? If we're multiplying by the same number every time. Now, this one, so we can plot these points, and we have -1, -2, we have 0, -1, 1, 0, and then 3, 2. So what do we see here? Yeah, this one's linear. So if we were asked to, we could draw the line. And again, if we were asked to on the exponential one, we could draw the little hockey stick shape. So if I did that, it would look something like this. Remember, we come close but never cross the axis there. So if I wanted to draw the line for this linear situation, it would look something like this. Okay? We weren't asked to here, but just to do it so that you can see what it looks like. And we see that those dots are all falling really close, if not directly on the line. So that's the idea on 6 through 11 on the homework. You're just plotting points and seeing what the situation calls for, a linear, exponential, or quadratic. So now we can also use the data without plotting on a graph to determine what type of model that we can use. So there's some things, very basic math that we can do here to determine what type of model to use. So the first thing we check is if the x values of the data have a common difference. So that just means, are we going up by the same amount each time? Okay. Yeah. So like, are we going for the x values -3, -2, -1, 0? If we're counting by the same number each time for x, great. Then we check the y. Okay. So if the y values also have a common difference, so if we're like adding the same amount each time for y, then that's linear. We talked about this back in chapter 4 and chapter 5. So this one would be linear. Common difference for x, common difference for y. We got a linear situation. Now I'm going to skip 2 for a second and go down to 3. If the common difference for x is there, so we're going like 0, 1, 2, 3, 4, 5 for x. Now we check the y, and we don't see that we're adding the same amount each time, but we are multiplying by the same amount each time. Then that is going to be exponential. Now, it's the quadratic one that's the new one here, okay? So if the y values first differences don't match, but the second differences do match. So what that means is this. By the way, this will be quadratic. Now let me explain what this means. So the first thing we do is we look to see if we're adding by the same amount each time for x. Okay, we are. Now we check to see if we're adding the same amount each time for y. But we're not. Okay? That's called the first differences. Now, if we now take those differences and we check to see if those numbers are adding the same amount each time, and they are, that's called the second differences, and that reveals a quadratic model. Okay? So that's what number 2 is talking about, and you will see an example of that down below here. So you'll see, if you don't quite understand what that means, you'll see it here in a second. So let's determine using these tables which type of model is best. So on this first one, we have -2, -1, 0, 1 for x. Those are changing by the same amount each time, so that's great. Let's check the y. We have 0.25, 0.5, 1, 2. Are those adding the same amount each time? No. Okay, so it's not linear. So now let's check exponential, because this is the next easiest one to check. So are we multiplying by the same amount each time?
Yes.
What are we multiplying by?
2.
Yeah, we're multiplying by 2. So 0.25 times 2 is 0.5. That's 1/4 times 2 is 1/2. Then 1/2 times 2 is 1. And then 1 times 2 is 2. Okay, so this is exponential. Okay, So now let's check the second one. First, check the x's. Are we adding the same amount each time?
Yes.
Yeah, we are. Okay, now check the y's. How much are we adding here from 9 to 5?
-4.
We're adding -4. You can think we're subtracting 4. I like to think of it as adding every time. So this is adding -4. Now, how about from 5 to 1? Adding -4. How about from 1 to -3? Adding -4. And then from -3 to -7? Also adding -4. So we were adding the same amount each time for x and adding the same amount each time for y. What is this?
Linear.
This is linear. So that's how that one works. Okay, so now let's take a look at the third one. We have, for the x's, are we adding the same amount each time?
Yes.
Yes. Okay, great. Now for y, are we adding the same amount each time there?
No.
No. All right, so let's check multiplying. Are we multiplying the same amount each time?
No.
No. Okay, so then maybe it's quadratic. So what we do is we go back to the adding. How much did we add to get from 1 to -1?
2.
It was -2. How much did we add to get from -1 to +1? +2. How about from 1 to 7?
6.
That's 6. How about from 7 to 17? 10. So obviously this is not linear, right? Okay, that's called the first differences. So now we check the second differences. So we do it again. How much do we add from -2 to 2? 4. How about from 2 to 6? 4. How about from 6 to 10?
4.
And notice that the second differences all wound up being the same number. Okay?
So it'd be quadratic.
That makes this quadratic.
Okay, now I get.
Yeah. Yeah, usually you don't really get what this definition up here is talking about until you see it happen.
Yeah.
Okay? So that's how you check quadratic. Linear is easy. Exponential is easy to see usually. Quadratic is usually the tricky one. So I usually don't check quadratic until the other two I've checked and I see that they didn't work. So then maybe it's quadratic. Okay? Any questions? All right. So when we're modeling real world data, keep in mind, like I said earlier, that usually the real world data is not going to perfectly fit along the line. The line that we draw is never really going to touch all the data points. Okay? So that means that we're not going to be perfectly fitting the data to a model. It's going to be somewhat off, and that's fine. So we can still decide which model is going to be best, okay? Even though it's not perfect, we're still going to be able to pick something that's fitting the data the best. So on this problem, we have a bunch of data that's given to us here. The value of a used car is what the data is representing. So they said which type of function is going to model the data the best. So we're going to use a linear one, a quadratic one, or an exponential one. And then they want us to graph it and write an equation for it, okay? So we're just going to look at the data here. We want the math to speak for it. We don't want the graph to speak for it because our eyes can deceive us, okay? So we're going to use the math. Now, first look at the years. Is the years, which we'll call x, changing by the same amount each time?
Yes.
Yes. Okay, so now we're going to go to the value of the car. Now, don't try to use the calculator to come up with this, just ballpark. How much are we changing from 12,575 to 11,065?
You can take 1,500.
It's like around 1,500. Yeah, okay. How about from 11,065 to 9,750?
1,200.
It's like, yeah,
1,200, 1,300.
okay, maybe around 1,300, right? How much are we changing from 9,750 to 8,520? Like around 1,200. How much are we changing from 8,520 to 75?
1,000.
It's around 1,000, okay? Just estimating. Now, if this is going to be linear, we have to be changing by the same amount or approximately the same amount every time. Did we do that here?
No.
Then this is not linear, okay? So that means it's either exponential or it's quadratic, all right? We ruled out linear. Does everybody understand that? Okay, because we definitely are not changing by the same amount each time. The amount that we're changing by is decreasing every time. So it's definitely not linear, okay? So now the next easiest thing to check is exponential. So what we're going to do is we're going to check to see how much this is being multiplied by each time. So in order to do that, because these numbers are kind of big, what we're going to do is we're going to actually take a calculator here, and we're going to take this number, 11,065, and divide by the number before it, 12,575. So you take your calculator and you do that math, 11,065 divide by 12,575. Control enter on your calculator so you get a decimal. What do you get?
0.87992.
Okay, so let's round it two decimal places. So you get 0.88. Okay, so now we're going to do the same thing for these two here. So now we want 9750 divided by 11,065.
Yeah.
0.88 again.
Oh.
Okay, so we want to check all of them because if these start to change, then we got not exponential. Okay, so we want the next one.
0.87.
0.87, and then the last one.
0.88.
Okay, 0.88. So now the question is this exponential then based on these numbers that we see?
Well, no, because of the one out.
We have real world data. Keep in mind that real world data rarely fits into a perfect situation. And these numbers are all almost exactly the same, okay? And we were rounding to the nearest hundredth, and rounding to the nearest hundredth, we didn't all get exactly 0.88. We were getting 0.87 something, 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 0.88 something, something, something. But when we rounded to the nearest hundredth, we got 0.88 on 3 out of the 4, and the other one was 0.87, which is really close, right? So can we say that this is exponential?
Yes.
It is pretty much fitting exponential, okay? So we're going to say that this is exponential. It's fitting an exponential model pretty good, okay? With the real world data, it's rarely going to fit better than what this is showing here, okay? So now what we need to do is write an equation. It says to write the equation for this situation. So the equation, if you remember, is y equals, if we scroll back to the very beginning, I don't want to do that, but if we did, we would see y equals
A
times b to the x. That's right. So now a is the starting amount. So we have y equals the starting amount, which was?
12,575.
That's right. What is that? 12,575 what?
Yeah,
Dollars. Now times b. And I told you what b is.
0.
It's the common ratio. It's the thing that you're multiplying by each time. And what are we multiplying by each time? 0.88. To the
First.
Whatever power.
It's the variable. So we can say x here. We can say t because it's years. I like t because we're talking about time. You can say x though if you wanted to, but that's our equation. Okay? It's very straightforward. You just take it right off of the data that you have. Okay? Now, we do also have to make a graph because it told us to. So we don't have any negative numbers, so we can put our axes in the lower left-hand corner. We've been doing that all year long. What's going to go on the horizontal axis?
Years. Time.
Yeah, the time, the years. And that makes the value of the vehicle on the vertical axis. Now, we only have data for years 0, 1, 2, 3, and 4. So I'm just going to spread this out a little bit and go every other line. So year 0 obviously will be on the axis. So this will be 1, and then 2, and then 3, 4. Now, for the value of the vehicle, I got to make it to 12,575. What should I go by?
1,000.
Thousands is great, so I'll label that up here. And then 1,002, 3, 4, here's 5,000. 6, 7, 8, 9, here's 10,000. Okay, and then it's just a matter of graphing these. So do the best you can with the scale that we have. So 0, 12,575, about there. 1 and 11,000, right around there. then 2 and 9,750, about 3/4 of the way, and then 3 and 85. About there. And then 4 and 75. About there. So after I'm done plotting these points and it's all spread out,
This looks linear.
it looks linear.
Well, but we can't really.
Is it linear?
No.
No, it's not linear.
It's not.
And here's how you know, okay? Now, you guys, if you had a ruler sitting in front of you, something straight, you could do what I'm about to do up here. I cannot take a ruler to this board because it'll get all messed up. But what I can do is draw a line, okay? If I try to draw a line through any two of these points, I will see very clearly. So I'll take this point right here and try to draw a line through that point and just extend it beyond. And you can see that those other points are curling away, okay? It's very clearly not linear because the other points curl away. And if I do the same thing from this dot up here first, and I draw it through the second dot, you can very clearly see that those other points curl away from the line that I'm trying to draw. It's just not linear, okay? It's hard to see before I do that. It looks very linear. But once you try to draw a line, you can see it's just not lining up,
Isn't it
okay?
because it's like so big, it's in such big numbers that like we're in like that little part where it just barely starts to curve.
It's so subtle that our eyes can't see it, okay, on the graph. But when you let the math over here, when you let that math speak for itself, then very clearly right here, oops, I'm still drawing a line. Very clearly right here, we can see it, okay? The math never lies, but the graph can lie, okay? That's why we let the math speak for itself. Okay, so now this one.
Same problem.
It's basically the same problem. We just have to look at the data and decide what kind of a model we should put on it, okay? So we have year, 0, 1, 2, 3, 4. Are we good with that?
Yes.
Yeah. So now we can look at the income. So now let's take a look at the income and be a little bit more accurate about it. What's the first type of model we should try?
Linear.
Okay, so if we're going to try linear, if we're going to try quadratic, we've got to try linear first, right? So let's check to see how much we're changing from year 0 to year 1. It's definitely not 600 something.
It's like 500.
Okay, I want to be a little bit more accurate than that. So actually do the math.
Oopsie.
Do the subtraction.
476.
476 is right. Okay, and then how about from here to here?
685.
6 what?
485.
485. Okay, how about from here to here?
480.
We're adding 480. Okay, and then the last one?
480.
We're adding 480. Okay, so we're checking to see if this is a linear situation. What do you guys think?
Well,
No.
It's
it
not,
could be because remember this is a real world.
It's a real world situation. Yep.
But it
but
starts
it's not
slow, goes high,
close.
and goes
It's
back.
not as close as we think it is.
Well,
It's not?
those are very close.
So 476, we got two 480s here. 485 is pretty close to 480. 476 is pretty close to 480. In fact, all of these numbers are very close to what? 480. This one's only off by 4 and it's 4 below. This one's only off by 5 and it's 5 above. The average number here is probably 480. Okay. Is this linear?
Yes.
Yes. We're not steadily increasing. We're not steadily decreasing. We're right around 480 the whole time. So we're going to say that this model is going to be linear. So now all we have to do is come up with two things. What are they?
Year and
No.
Equation.
We have to come up with the equation. So y equals, what's our model for the linear situation?
Y equals mx plus b.
Okay, y equals mx plus b. What is m?
M
No,
Right?
no. What does M represent? What's that letter? What? It's the slope. Slope is another word for a 3-word phrase. Starts with R.
Real world.
Okay, rise over run is a what?
I don't know.
It's a rate of
Change.
change. There you go. It's the rate of change. Okay. What's our rate of change here?
480.
480. We're changing by about 480 every time. So guess what?
So
That's it.
That's our slope. Yep.
It's 480 times a year and then plus 18,250.
Where'd you get the 254?
It was starting. That was just starting.
Yeah. The B is the y-intercept. That's where we start when time is 0. When time is 0, that's our y-intercept, 18,254. It's that easy. Okay? You got your slope already because you already know the rate of change, and you already know the y-intercept because it was given to you. It's that straightforward to come up with an equation. If you remember back in chapter 5, we had to do this whole huge process to come up with the equation. And now, here we are in chapter 9, basically just lifting the equation off of the data because we already know the rate of change and we already know the y-intercept. So there it is in the equation. Okay? It's kind of nice. Now, we still got to make the graph. So do we have any negative numbers?
No.
Okay. So axes in the lower left corner. What's going on in the horizontal?
Years.
Sure. And then the income, so the money, is going on the vertical. And how can I make my scale for years?
Every other line.
Sure, every other. Okay. So we can go 1 here, 2, 3. Just got to make it to 4. Now, how about the scale for the income?
It'd have to be by 2,000 or 1,500.
By 2,000 would be better.
Since it's 14 lines, you can.
Yeah, we got to make it all the way to 20,000 here, so we got to go by 2,000. So 2, 4, 6, 8. Here's 10,000. And then 12, 14, 16, 18, 20,000. Okay. So now we're going to plot these. Just kind of watch your scale there and make sure you're trying to put these down pretty good. So we got 18,254. So 18,254, probably right around there. 18,730. 19,215. 19,695.
Oh, crap.
Almost 20,000. And then 20,175, just over 20,000. Now, if I go to draw a line on there, should my dots be very close to that line? Should they be curling away like they were in the last problem? I shouldn't see that, right? So if I go to try to draw a line on there, like if I don't need to draw a line, it didn't say to draw a line. I'm just putting this line on there to check, okay? So you guys shouldn't have a line on this problem because it didn't say to do that, all right? I cannot put a ruler down, and I can't do that on the video, so I'm putting a line on here just to see. And there you go. Okay. So that's what that looks like. And it does look like the dots are all falling along that line, which is great. That's what we expected. So it sure does look linear. The data over here, the math was showing linear for us. We made the graph. It looks linear. This is linear.
They're not always going to be accurate.
Okay. So that's the whole section. It's not too bad. It's not too long. Pretty straightforward. It's kind of math you've already done. Okay.